Good morning, everyone. My name is Brendan McGinty, and I am moderator for the session today, another seminar from our Center for AI Innovation within the National Center for Supercomputing Applications at UIUC. We are very happy to have Dr. Bo Lee with us today. As a reminder, before I introduce Dr. Lee and continue with the seminar, questions can be asked in the chat. We will try to leave some time at the end for some of those questions and aim to end at top of the hour at 12 noon Central Time. So let's go ahead and get started. I'm going to introduce Dr. Lee. Dr. Bo Lee is an assistant professor in the computer science department at the University of Illinois at Urbana-Champaign. Her research focuses on machine learning, security, privacy, and game theory. Specifically, much of her and her lab's work aims at exploring vulnerabilities of machine learning systems to various adversarial attacks and endeavors to develop real-world, robust learning systems. It's a pleasure to have you here today, Dr. Lee. Go ahead and take it away.
Yeah, thank you. Thank you for the introduction. It's a great honor for me today to share my research on the trustworthy machine learning, especially the secure learning adversarial environment here. Let's get started. So as we all know that the machine learning has been ubiquitous in the world, which has been applied to different domains to make our life better. For example, of course, autonomous driving, intelligent medical treatment, smart city, etc. And also many like security critical areas, for example, malware classification, fraud detection. Machine learning is already applied to different kind of these types of domains to protect both business and personal information. However, we also know that there are actually even such very powerful machine learning techniques have already been attacked or leaked private information, which brought like security and privacy problems. For example, one real-world example is in 2016, the Associated Press Twitter account of White House has been attacked, spreading the rumor that the White House has been attacked. And this fake news actually has triggered the autonomous trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within seconds, which is like a huge loss in real world, which is one of the real world types of adversarial attacks from the NLP perspective. And similarly, in the Australia airport, the biometric recognition system have been deployed for safety screening, which also raised a lot of privacy concerns regarding the database leakage, like learning gradient leakage, and etc. So we can see that even though we are living in a quite convenient and efficient and nice world with a lot of good platforms for us to deploy different machine learning techniques for training and testing and analyzing our own data set, etc. We are still living in an adversarial environment. Therefore, a typical machine learner still have a very hard life to build so-called secure or trustworthy machine learning platforms. Therefore, we need to sit down together and indeed try to understand the properties of adversaries. For example, their ability, their goals, their constraints, and their strategies, etc. And then develop the secure and the trustworthy machine learning platforms against such diverse different types of attacks. Before we dig into the details, and one question people may ask about, currently there are a lot of word or sentences talking about trustworthy machine learning and fairness, privacy, etc. So people may ask, what's exactly one fundamental question, right? And what could be the fundamental causal reasoning for such adversarial behaviors? So I would say on the very, very high level, we know that traditional machine learning approaches usually assume that the training and testing data are drawn from the similar or even the same distribution, right? That's why we can train on one data distribution and test on the other. But in the adversarial environment, usually either the training data distribution can be manipulated such that it can generate the so-called poisoning attacks, which means some real-world example is that if you have, say, the Netflix recommendation systems or your Amazon recommendation system or like Yelp recommendations. So usually, for example, people can easily create some fake account and generate like fake comments and fake ratings and etc. So these types of attack can be so targeted so that they can say promote certain movies or demote certain items, etc. So this is one type of training data attack called poisoning attack or backdoor attack, and similarly. Or on the other hand, the testing data distribution can also be manipulated, which is usually called evasion attack, which means even though you have the ability, for example, to train like machine learning model and protect it, like we guarantee our training data is clean, it's still very hard to guarantee that our test data is clean. For example, if you have a well-trained like malware classification or detection system or software in your computer, then the attackers can manipulate the malware and generate some like variants of the malware and bypass the detection system and still do harm to the computers, the machines. So this is called evasion attack. So on the very high level, I would like to say that basically in the adversarial environment, if the data distribution, either training or test, is adversarially shifted, it will generate these types of adversarial behavior. And our goal is to try to understand these types of shifting and try to make sure the machine learning model can still provide trustworthy or even explanation for the predictions given such adversarial data distribution shifting. So I would say this is one fundamental key in trustworthy machine learning. Yeah, so based on this, we can see that our goal of my research or our lab, which is called Secure Learning Lab, is design the certified, robust, private, and expandable machine learning paradigms. Realize that it's not only robust, it should be certifiably robust, and we can discuss what does that mean. So basically, we can see if given a traditional machine learning pipeline, starting from the input, pre-processing, model selection, and post-processing, and some final output. And first, we explore what's the potential adversarial attacks, either evasion or poisoning, as we discussed, to identify the vulnerabilities of the machine learning pipelines. And then we develop the robust machine learning models, either by incorporate human knowledge or use ensemble models, or developing different training strategies to provide the certification for the robustness. For example, it either can happen during the pre-processing, like identify robust features and robust transformations, etc., or during the post-processing, we can leverage some game theoretical analysis or leverage different intrinsic or extrinsic information in data and the learning tasks to improve or certify the robustness. And the certification here means that we provide a lower bound of accuracy under certain constraints, which we will discuss more later. And of course, another thing is we hope our machine learning pipeline is explainable and can certify some other properties such as fairness, ethics, etc. And one very interesting thing is like the user quantitative data valuation to identify or understand what's the machine learning explanation for different data contributions, which is one famous term for Shapley Value, which I will briefly introduce a little bit later. And finally, we focus on the privacy problem, like what's the potential attacks or privacy leakage given the trained machine learning model or even just the embeddings, and then how to protect the private information against such well-trained machine learning models. So in this talk, of course, you can see there are a lot of very exciting topics. I cannot finish all, and I will mainly focus on 3 topics, and hopefully can give you we can discuss some overview here. And if we are interested in certain details, we can discuss more. So first, I will show some interesting examples of real-world adversarial attacks in case some people haven't seen, so can have a feeling that what what attacks we are talking about here. And the second, I think, is also the most important part today is about how we can leverage knowledge or like a kind of like logical inference to improve or certify the robustness of machine learning pipelines. Not a single model, it's a pipeline against such adversarial attacks. And finally, we'll touch a little bit about how to use data Shapley to give contributions or valuations to the data. So if we have certain results, say we know the accuracy is high or the robustness is low or whatever, we know how to trace back to which data point lead to such result. Therefore, we can clean up or relabel or dig into inspect what's the problem of our data or even the pipeline in our machine learning even the component within the whole machine learning pipeline. So first of all, let's look at some real-world attacks, and let me know if there are questions. I can check the chat. Also, you can unmute yourself. So basically, we know in digital world there's a lot of different types of attacks, and you can see this simple example is that if you have an image which is correctly classified as a cat by a machine learning model, but if you add a very small magnitude of perturbation, just like here you multiply 0.001, which is very small, and add to this image, and it ends up you have this image. And for human, these two look exactly the same, right? I cannot see any difference, but exactly this image will be misrecognized as a dog, which is an adversarial target. You can target to arbitrary classes, which is not a ground truth cat. So this is quite dangerous because in this case, even human look at it, I cannot recognize this is some manipulation or attacks, right? It's very hard to identify it. But this is in the digital world. And then the question is, what harm, how harmful this could be, right? Whether such attack can be transformed to the digital world and make potential real loss, like in the stock market example we just see. So this is in real world, say if we have autonomous driving vehicle, the autonomous driving needs the perception to identify like pedestrians and like road signs and obstacles, etc. Then the question is whether we can generate some real world attacks against such, say, autonomous driving vehicles or other like household robotics and etc. And one interesting observation is that in real world, there are some stop signs or road signs which contain a lot of interesting graffitis. For example, this is take the image taken from Vancouver and the right-hand side taken from Berkeley. So you can see different stop signs actually have different like graffitis and things, which triggers us to think, what if these types of real-world triggers are actually adversarial, right? And for human, we actually will not recognize them as adversarial and will not replace them, which can be dangerous. But before we dig into it, we can see some additional challenges to generate such real-world adversarial attacks. For example, compare with the digital one we have just seen, which we can like just solve a nice constraint optimization and optimize this noise, right? In physical world, there are additional challenges. For example, there are different like physical conditions like angles, distances, and lightnings, how you can ensure your attack can be resilient against different conditions. This is one thing we need to think about, because in digital world, we don't have this worry. We exactly know, or we can insert the accurate, like precise pixel value to the machine learning model, right? But here, the pixel value can change under different conditions. Right. And the second is, as we see in the digital world, the perturbation itself is invisible, right, to be stealthy. But in physical world, we actually do not hope it's invisible, but unnoticeable, right? Otherwise, if it's invisible, like the autonomous driving cameras or things can also cannot capture the perturbation. But we hope the physical cameras, etc., can capture the perturbation and be fooled. Right. And the third is, of course, there are different fabrication errors in real world that if you, for example, if you want to print out some perturbation, if what you want is a red, but actually what you have is a pink one, and then the camera see it as orange, right? So these types of physical conditions is very messy. And the last one is in digital world, we can add perturbation everywhere to the whole image, right? But in physical world, we cannot add, say, background to the noise to the background, right? So therefore, we can only find the object and try to add a perturbation onto the object itself. So how to make this happen, right? So in order to address these challenges, we can briefly see what's the tricks to address them one by one. So first of all, at a very brief, I think this is a very generic way. So I need to put this equation here, which is if you want to generate a digital perturbation, right? That's like standardly how you do it. So basically, you find the delta, which is a perturbation, right? And you want to minimize the magnitude, the LP norm of the magnitude of the perturbation so that it could be invisible in digital world, right? And such that this perturbation will fool the machine learning model F theta, which is a victim model, right? And X is the original instance plus this delta. So this will be the perturbed instance. And so this whole prediction will be fooled into this Y star, which is the adversary target, which is different with the ground truth, right? So overall, we want to minimize this combinatorial optimization in digital world. But in physical world, how it can be done, right? Considering the challenges we just mentioned. So first, we want to deal with the different physical conditions. So basically, we can see if we want to make sure the perturbation is effective under different conditions, we hope that we can sample different constraints. For example, here this represents different like lightnings and distances and angles, and this will be we call it like transformation, distribution over transformation. So basically, we generate synthetically generated different transformations, which can be viewed as different distribution in real world, and then sample them as xi here. And instead of optimizing this single loss function, we optimize this whole big loss function, consider different xi under different conditions, and then add the delta. So this we will view it as a so-called like the universal perturbation, that the delta will be effective under different condition xi so that it can be fooled under different conditions. And with this, we also want to ensure that the perturbation itself is spatially constrained and visible, but not noticeable, right? So the second thing we want to do is we want to add a spatial mask to the perturbation itself, such that the perturbation can be only optimized within this mask. And of course, this mask can be of a meaningful shape, like Mickey Mouse head or apple or like that. Therefore, we can make sure the attack will be of meaningful shape, therefore will not raise human attention, but it is stealthy enough, which is called hide in the human psyche. And basically, there are some tricks to identify such masks. For example, in this loss function, we want to use, say, some sparsity loss, like L1 loss, to find the vulnerable regions within the instance first. And then within this vulnerable regions, we can generate certain meaningful shape masks. And then we use like L2 or TV loss to smooth out the perturbation. And therefore, the perturbation will look with meaningful shape, but very smooth. So it can be appear to be stealthy to human vision systems. And of course, in the end, we want to solve the fabrication error by adding another loss term to minimize the distance between the generated perturbation range and the real world, like say the printer's printable range. So by solving this like losses by adding different loss terms, we can see some examples directly. So basically, you can see all the stop signs on this slide are misrecognized as a speed limit sign 45, which is a targeted attack, we call it. And the right-hand side here is misrecognized as a stop sign, which could be very dangerous because you will suddenly stop at this sign, right? And you will never stop at stop sign. And the different columns shows different types of physical perturbations, and different rows show different conditions. And you can see that the first column shows some like fading out, stealthy perturbation, but actually it is adversarial. And the third column shows some love and hate letters. And I think the last two rows are the examples that people quite like to use is just as black and white rectangles are enough to fool such machine learning models by misrecognizing such stop signs. But of course, you can see these are after smoothing, so they become pure black and white, but not always for any object. Only white and black is enough. This is like by accident for these types of stop sign, these types of perturbations is enough. And of course, the positions of such like perturbations are very important. If you move the position of the blocks below or up above it, then such perturbation will not be quite effective. Therefore, a key in physical world is that you can slightly enlarge the regions of the perturbation so that to remain effective under different conditions. And of course, we on purposely do not cover the letters like stop here. Otherwise, it will be meaningless, right? So this is a static analysis or evaluation for such physical attacks. Let's see some real-world examples or testing. So we can see we indeed drive a car towards these types of sign, and we can see that on the left-hand side, it's like one of the physical perturbation we have seen. On the right-hand side, it's a control experiment. And from the caption, you can see on the left-hand side, it's consistently misrecognized as bit limit sign 45. But on the right-hand side, it can correctly recognize it. And this is another example with a fading out, and you can see similar performance that the left-hand side can always be misrecognized, which means even you drive a car towards it with different angles, speed, conditions, these types of physical perturbation is still quite effective against the well-trained machine learning model. So this example is against the classification or classifier, right? And the question is, later on people ask a lot of interesting questions, say whether we can use such physical attack against the like object detectors or other types of machine learning models. And actually, I do have a class show that all types of machine learning models, as long as you name it, it's very easy and very possible to attack it. And here is just one example, like the physical attack onto the stop sign we have just seen can also attack these types of object detector, which is called fast RCN. And you can see all the other objects can still be correctly recognized, but this stop sign cannot be recognized until you get very, very close to the sign. So that kind of you can recognize this purple box with because you recognize the digit, because we on purpose do not cover the digit, right? But this is too late for a car to stop with such a close distance, right? And another question people ask is, okay, this is effective against different types of machine learning models. And what about, this is so far is all white box attack, right? Meaning that the attacker can access the parameters of machine learning models, like the F theta we have seen, right? We exactly know the theta. So the next question is whether we can perform such attack with black box attacks, which means, so there are a lot of ways to do black box attack. And one direct way is so-called adversarial transferability, which means if you attack model A, can you use exactly the same perturbation attack model B, which are of different architecture, parameter, even training data, etc. Right? And we can see we exactly use this example and test against this YOLO, which is a different object detector here. And we can see still in this different environment, you cannot recognize the stop sign until you get very close to it. So it means that even though the black box attack in this case is very successful, and you don't need like a clear information about the black box model itself. And there are a lot of interesting analysis about this adversarial transferability as well. For example, we actually calculate the upper lower bound of such transferability under certain conditions. And yeah, if you are interested, I can also point out some literatures later. So far we can see these types of physical adversarial attacks and real-world attacks is quite successful, and it has been such stop sign. Very interesting, it has been exhibited in the Science Museum of London, and a lot of people play with it, and I think this really raised the attention of the general community, and see the trustworthy machine learning is really important in our daily life, so that we can trust the AI like equipment and every like robotics or things around us, right? Because I think everyone has more than like 5 machine learning or AI equipment already around you. So with that, another like very interesting question people ask is, if we want to attack autonomous driving systems, right? So far, all we talk about is the vision systems. And in reality, the autonomous driving system have other equipment for perception only. For example, they have LiDAR, they have radar, they have all kind of like sensors, fusion models. Whether we can attack those models, it's another question. So here I will very briefly show some examples to see that actually such real world like even LiDAR systems or sensor fusion systems can be attacked effectively. For example, this is a high-level structure of the open source Apollo autonomous driving system, like LiDAR recognition pipeline. So basically, you can see that a lot of complicated and connected component for the LiDAR recognition system in Apollo system. And they are not a single end-to-end model, right? They have different component feature extraction and then pre-processing, post-processing, etc. And the detail here is not very important. So my point is that even given such pipeline which is not an end-to-end machine learning model, we can still do the optimization against it, such that the goal is to generate some adversarial objects. And in real world, such adversarial objects will fool the LiDAR system in the sense that the LiDAR will not recognize this object, even though it's just put there on highway or anywhere, right? So we hope we can generate something like this so that the LiDAR system will never detect such objects. So we can see a real world example is that now we optimize this real world 3D object. And the key to optimize that is the difference with the 2D image is that in 2D image, you optimize the pixels, right? And in 3D image, you have a little bit more degree of freedom because you can view it as a 3D point cloud. And therefore you can manipulate the point distance, and then you can also add or remove some points in this point cloud. Therefore, you have slightly more freedom to optimize this 3D object. Of course, it also is a little bit more challenging, but I want to show that even though it's more challenging, it's quite possible. There is a question. Okay, sure. Yeah, so if you have a question, let me know. So basically, the example we can see that we optimize this 3D object and then 3D print it out and put on the highway. And this is an adversarial object. This is just a box with similar size as a control experiment. And you can see when we drive the car towards it for this adversarial, this LiDAR can never recognize this object itself. But in the control experiment, you can see that if you drive the car towards this box, there is a green box, which means that the LiDAR system always recognizes this object. So similarly, we can see if we put this object onto different positions, like this is a straightforward front, and we can put it on the right-hand side, and we can observe similar behavior that this box can never be recognized, but this control experiment can see this green one. Basically, it means that the control experiment can recognize this object. So basically, you can see this LiDAR system can exactly be would like to assume you present a write-up. Yeah, I can show there's a question in private chat for the presentation. Yeah, I can later on share the slide. So basically we can see the LiDAR system and the camera system individually can be attacked. And of course, there are a lot of new papers talking about, can we use sensing like sensing fusion systems to attack the machine learning models or actually protect the autonomous driving vehicles, right? But similarly, we can want to show a very quick example that with a reasonable sophisticated pipeline, for example, you consider both the point cloud and the image together and optimize them together, and then you add some stealthiness constraints to make sure the generated object is not only in terms of the shape is stealthy, but also in terms of the appearance have some like patterns on it to be stealthy as well. You can actually easily attack the sensing fusion system as well. Therefore, you can see we can put such like a drone cone, which is very common on highway, and this is actually optimized one. You can see the pattern is a little bit weird, but actually not that obvious and on the highway. And some very interesting example is that you can see on both this LG simulation platform and Apollo simulation platform, you can see there's the object. You cannot recognize it and the car directly drives through it. But in the control experiment, if the car recognizes it, it will stop at the object. So that means in real world, if we have such like adversarial object, it can actually attack the sensing fusion systems easily and leading to potential severe consequences. And if you want to play with more examples, there's a website and we have other example and simulation platforms to play with. And actually so far, a lot of vehicle companies have recognized such like based on the work, recognize the vulnerabilities and integrate such testing to test the safety and the trustworthiness of autonomous driving vehicles. And I think it's very interesting to see what we can do in terms of protecting against such protecting the machine learning models against such attacks. So far we have given some very interesting examples of attacks in physical world and the digital world. And then the question is how we can protect against them, right? How we can improve the robustness of machine learning models. So far there are some, not some, actually many defense methods proposed, either detection or defense or other method to improve the machine learning models robustness. And unfortunately, these types of methods so far focusing on the empirical robustness, which means we can, like say, do adversarial training, that we put the adversarial examples or attacks we have seen before into the pipeline to retrain the model again and improve the robustness. But this way, we can see it's possible if I have a new attacker, I can generate a new adaptive attack against such systems. So in the end, maybe we can have some traditional security cat and mouse game. You have new attack, I have new defense, and again, you can have a new attack. So how to end this game is a very important topic. Therefore, there is I think it's only like this 2 or 3 years started, but grows very fast, this domain called certified robustness. So the content here is a little bit small, but I want to put everything here, give you a sense. Basically, it means that in terms of the certified robustness, which means you can not only provide the empirical robustness for machine learning models, but also provide certification, which is a lower bound of the accuracy of your model, which means I can guarantee you that your camera on your autonomous driving vehicle, the accuracy will be will not be lower than 95% as long as the attacker satisfies certain constraints. So in terms of this, you are more trustworthy and happy to use the car, right? Otherwise, if I can tell you in this testing environment, it's 95%, you never know in other testing environment what's the accuracy. It potentially could drop to 1%, right? That way it's very dangerous and uncertain. So in this long, like a big tree, there are different ways, like a deterministic way, probabilistic way to give certification. But even though we have a large branch or numbers of literature here which achieve very promising result about certified robustness, there is one common drawback or limitation here is that in this deterministic branch, which usually apply different types of constraint optimization method to solve this min-max game, right? To improve the robustness of the machine learning models. This branch is not scalable to large scale neural networks. For example, if we use some tools, say SDP or certain things, we can only scale up to 3,000, less than 4,000 neurons. And if we use other, so far all the methods under this deterministic branch cannot scale up to, say, the ImageNet scale of data set. And only the branch, which is a probabilistic branch, give you the probabilistic certification, can scale up to ImageNet level data. But still, all of the methods here can only certify a relatively small magnitude of perturbation, which means as long as the attack, as we discussed before, right, we can measure the magnitude of the perturbation. As long as these types of perturbation magnitude is smaller than something, we can provide the lower bound of the accuracy. But this magnitude so far is very small. For example, in terms of our tool, we can only certify in terms of 0.5 on CFAR, but the accuracy lower bound is around 60 or 70. And if you want to certify around 90, then the L2 norm is still need to be smaller. So the question here is, can we use additional information to improve such certified robustness and certify a larger radius of perturbation and potentially larger machine learning model as well? So this is a key question we want, right? We want to ask. But in order to solve that, we definitely need to leverage additional information. So my point of view is that currently for our machine learning models, we always focus on the data-driven, pure data-driven types of machine learning models. But there are a lot of information that is not modeled by our data yet, right? For example, our human knowledge, our inference, logical ability. So you can see all the examples we presented so far, human cannot be attacked, right? Only machine learning model can. So how can we leverage some human inference ability to improve or certify high robustness of the machine learning models? So that's a key question. So here I want to say we can leverage either the extrinsic information, such as the domain knowledge, or some intrinsic information, such as the spatial and temporal consistency of machine learning models, to improve or certify the robustness. And here, back to the main topic here about the sensing reasoning pipeline, which incorporates domain knowledge into a machine learning model. So here, I would give some high-level intuition and the pipeline about how this works. And in terms of detail, there are actually a lot of interesting detail. For example, different reasoning component, etc. We can discuss more later on. So on the high level, I would say instead of a single neural network, can we leverage a machine learning pipeline to incorporate the domain knowledge to improve the certified robustness of a machine learning pipeline, right? And the pipeline here looks like basically we can train multiple single statistical machine learning models. For example, we can train multiple neural networks, or we can train multiple, it can be either neural network or logistic regression or any traditional machine learning models. And each one will take an input instance as an input. And then their predictions will be connected by some component. And this component, we call it a reasoning component, which means these connections following some domain knowledge logics. For example, we know if this is a cat and the cat belongs to the mammal category, or cat cannot swim, or cat has a tail, some properties, right? We know, we humans have such common knowledge, and we can embed such the common knowledge into a first order logics, say a stop sign infers an octagon shape, right? Such things. And then with the first order logic, we can easily embed it into a probabilistic graphical models. Either it's a Markov logic net or Bayesian networks, etc. And then with this end-to-end pipeline, which we call it the sensing part and the reasoning part, we can certify this robustness from the end-to-end purpose, which is this eta is, say, let's call it the input perturbation magnitude, which is the same with the perturbation magnitude we saw before. And with the traditional method here, like all the method we discussed, we can certify the output of this single neural network epsilon here, right? And now we know what's the uncertainty of the output of each single neural network, and we give this to the whole reasoning component. And our hope is that this reasoning component, since it incorporates logics and domain knowledge, it can further correct some incorrect predictions from here, right? Therefore, these incorrect predictions can, because we need everything satisfy the logics we know, right? So after satisfying these logics, we can correct some incorrect predictions, and therefore we certify the end marginal prediction probability here. So we know, given the magnitude of the input perturbation, what's the uncertainty of the marginal prediction probability of the output of this whole pipeline. So this is a goal, right, to certify it, so that you can see why certification is important, because it gives you an exact certainty about, given certain input magnitude, what's the uncertainty of the prediction with guarantee. And therefore, we can see the intuition is that it should be hard for attacker to generate an attack that still satisfy all the logical relationships, right? If you attack a statistical machine learning model like neural network, it's easy. But if you still want the attack satisfy certain complicated constraints, it should be harder. And therefore, maybe it's like more robust for the machine learning models. So here we can see formally we want to certify the robustness of this whole, like this Q is the, we can view it as a query function, and the sigma is some perturbation. After the perturbation, this pi alpha and pi alpha prime samples represent this true distribution, right? Remember at the very beginning, we see that adversarial machine learning represent this adversarial distribution drift problem. And now we exactly want to sample this true distribution, as long as this true distribution is bounded by certain things, constraints, which is the attacker's constraint, right? We want to know this prediction probability is bounded by this delta, and we want to calculate this delta. And the problem itself here is quite clear, but there are a lot of challenges for it. For example, if we use like graphical models, the inference time, for example, for MLN itself is Shapley complete, right? The Markov logic network in terms of the inference itself is Shapley complete, but given this completeness of the reasoning component, one opportunity is that it actually defines very nice exponential family with nice property, for example, non-negativeness for the weights and the monotonicity of the models, etc. Therefore, I can show very quickly about leverage such nice properties. We can actually give a very tight and straightforward certification bound, which is quite useful in practice. So before that, we can see slightly more concretely how we can build this sensing reasoning pipeline, right? So give an input, say a dog input. We have different sensors, recognize whether it's a dog, whether it's a cat, whether it's an animal, and then the logic is dog and cat both belongs to an animal, right? For example, if this sensor tells me this is a stop sign, right? And then this logic will be violated because the stop sign is not an animal, right? So such types of things. And of course, we have different ways for the factors here, and we have like these types of factor, which is the interface factors connecting with the sensors, and the real factors inside the representing the logics. And we can train these inter-real factors ways. And therefore, the end goal we want to achieve is that given this MLM program, right, how many the grounding assignment can be true or satisfying the logics here. So basically, this Z2 representing all the possible words in this like graphical model. And then this Z1 means how many of them are true, like satisfying the ground truth logic rules. And we want to calculate this probability. And this is eventually the uncertainty of the prediction probability that we want to present. And therefore, we can see that in order to bound such probability, first of all, this itself is a very hard problem. For example, there is a very famous like Shapley complete problem called counting, that the goal is that given certain query functions, and we want to find the constant real number z such that it satisfies this upper lower bound, right? And we can see from this formulation, it can easily write our robustness certification into such format. Therefore, we can easily show this counting problem can be reduced to the robustness problems we want to achieve, which is slightly unfortunate news, is that our robustness problem itself is Shapley complete. So it's very difficult. But still, with some additional assumptions, we can achieve some result, and we can see. So basically, we can see general robustness is hard, MLN is hard, and for like say even like tree structure-based Bayesian networks is also hard, but we can still make additional assumptions to achieve some result. So basically, here we can see the hardness really comes from the graphical model inference time, right? Can we say we have some oracle, assume we have some oracle of this reasoning component, whether we can do better, right? So basically, the thing is that if we have a MLN robustness problem that we want to achieve, so you can see previously, this problem is hard, but assume that we have some oracle for this Z1 and Z2, right? For this Z1 and Z2, we can see the oracle equals to the ground truth Z, which is hard to obtain, plus some weighted noise, right? So this Z delta becomes our estimated output of the probabilistic graphical model. Right, these are the oracle inference. So we can see if we assume we can access such an estimation of the true output of the graphical model, then we can do something very nice. Basically, the first condition is that if this lambda is always larger than 0, we actually know, we can prove that this D delta is always monotonic, either increasing or decreasing, it doesn't matter. This way, we can always select the upper or lower bound of this max or mean, which is lower bound and upper bound of the prediction probability that we want to bound, right? By instantiate at the two the positions, which is the CC is the magnitude of the perturbation we can tolerate, right? So always we know this because this is a condition for the attacker. So we know if it's monotonic, we know this max and mean will be achieved at both minus C and C. So we can exactly know what's the upper lower bound of this marginal probability. And the same if the lambda belongs to -1 and 0, rather than larger than 0 or smaller than -1, this thing is not no longer monotonic, but we can prove it is convex, so that we can still achieve the optimal value at the point. Basically, we can sample among -C to C and achieve the 0 gradient, and therefore achieve the optimal value. So basically, it's if the lambda is belonging to this regions, it is the model itself is convex, so that we can still achieve nice bound to bound this upper lower bound. So you can see here, based on these types, one assumption, which is we have oracle access to the reasoning component output, and the one is we can instantiate the noise noise coefficient here, we can exactly analyze the property of the models. That's what I mentioned the opportunity before. Even though we have challenge about graphical model, we have nice opportunities for them because they have nice structures, and therefore we can achieve like a nice analysis for it and give the strict upper lower bound for this probability marginal prediction probability. And similarly, we can do this for Bayesian network and etc. And let's use 3 minutes to look at the examples here. So basically, say we want to have this primate net. Basically, we want to identify different categories of the images here, right? And they have some nice logics or knowledge. One is that they have, for example, in ImageNet, these types of structures is already labeled for different categories. So we exactly know these 2 types of knowledge. One is called hierarchy knowledge. Basically, it means that if you are greater Apey, you exactly belongs to Apey, right? And the exclusive knowledge, which means if you are greater Apey, you should not be lesser Apey anymore, right? These types of exclusive one. So you can represent them as a first order logic here, and embed such knowledge into a sensor reasoning pipeline, as we mentioned before. And the very nice thing from the result is you can see, usually we know there is a trade-off between benign accuracy and robustness, right? But here, we can see even with knowledge, such trade-off is largely relaxed, that even the benign accuracy is slightly higher than without knowledge. And of course, in terms of the certified robustness, it's like almost like doubles the certification of the traditional robustness. So basically, this sigma means the smoothing parameter, which is used for standard certification method. We don't need to care much about it. It just means with larger smoothing variable, the model is smoother, which has higher ability to achieve robustness. And we can see the certification with the knowledge by injecting such reasoning component is dramatically significantly larger than the certified robustness for a single neural network machine learning model. And this alpha here shows how many % of the like sensing models are attacked. Right, you can see up to 50% of the sensing models are attacks. You can still certify relatively high robustness. And some interesting observation is that not only this types of sensing reasoning model can correct the prediction, but also it can correct the prediction with very high confidence. So the green part means the prediction is correct, and the y-axis shows the confidence. And you can see it actually is not only correct, but also very confident because you have the knowledge. So usually it's very confident. So that's a very nice news and a nice property. And similar with a more concrete example along the stop sign example we sent before, that we can generate such a pipeline, which is another example that you can give a road sign to different sensors. For example, it recognizes whether it's a stop sign, whether it have the like stop patterns, letters, or whether detecting the shape, that whether it's octagon shape or not. And everyone can connect with like a graph neural networks, graphical models. For example, if you are a stop sign, you should infer its octagon shape, right? Or if you have a stop sign pattern like S, you should infer you should be a stop sign like this, right? And I will not go to details, but we can easily see the certified robustness of such road sign recognition in terms of benign accuracy is quite also high. Almost there is no trade-off between robustness and accuracy anymore, which is also quite reasonable because we add additional information to the machine learning model. So it's reasonable that we achieve better performance, right? Both benign accuracy and robustness. Like this bar shows, compare with the, say, the state of art. If it's higher, it means you are the knowledge pipeline is higher. We can see almost all the numbers here are higher, and the x-axis, the number is the index of different types of attacks. You can see up to 46 types of attacks, including like all the attacks we mentioned before. Like I will just quickly go through. So basically, like the physical attack we have seen, and some infinity or attacks we seeing, or like unforcing attack like JPEG or snow or frog or whatever, and even some common corruptions, brightness, etc. So because this pipeline is attack agnostic, you can see, right? So it's very possible to generate this robust pipeline against all the different types of attacks, which is very promising. And so far we have seen all types of different attacks and how to improve the robustness against them. And in the end, I want to use 1 minute, which is not very important, but I think a very interesting topic to know is that how we can give valuations to our data. For example, we know the data currently is very important, right? Like everything belongs to data. And we really want to know which data point is more valuable than others, right? So therefore, there is a very nice term called Shapley Value. Basically, we hope our data valuation is quantitative rather than just some saliency map and human can see or understand it, which requires some manual work, right? We hope we get some quantitative numbers. We can exactly see, oh, this data point is more valuable than the other, right? But how to define it? These are some properties for the data valuation we need to satisfy. And a unique solution to satisfy all these properties is called the Shapley value, which is a concept provided by Nash, which wins a Nobel Prize, right? And this is for from the game theoretical analysis, view each human as a participant. But in our machine learning world, we can view each data point as a player, as a human in a game theoretical analysis, right? And we can exactly calculate the contributions of such data by using the term of Shapley value. Basically, you want to enumerate all the combinations of the data set and calculate the marginal contribution of this data point. For example, with and without this data point, what's the difference? And therefore calculate the Shapley value. So it can be used for a lot of different applications and machine learning pipeline debugging. So, okay, so far I think we have hopefully convinced you that the security and privacy problems are very common in machine learning models. And in order to improve the robustness, there are different things we can do. And still, it's an open direction and very nice to dig into it further. And we also hope we can have efficient data valuation to provide us better understanding about our data and the machine learning model. Yeah. Thank you, everyone. Welcome to ask questions.
Dr. Lee, an amazing, detailed, inside look to how you do your work and the prowess of your research. We don't have time really for questions unless someone has a quick one. I am going to encourage people to look at the recorded presentation, which will appear in a couple of days on our website, and to reach out to Dr. Lee directly with questions, if that's okay, Dr. Lee.
Sure.
I would assume that it is. If you have any trouble reaching out to her, I'm happy to have you reach out to our center, and we'll put you in touch with her. Again, the presentation will be available. What a great presentation on our website. Anyone have a quick question to conclude today? And if not, we will we're right at the top of the hour. Dr. Lee, we really appreciate your presentation today. And please reach out to her with any questions. Thank you very much. You're already getting some great comments in the chat. Thank you again for being here.
Thank you.
And we will hopefully see you next week as well. Thanks.
Yeah, thank you. Yeah.
All right, thank you again.